Welcome to the deep dive. This is where we jump straight into complex topics. We do the reading, the sifting, so you get the core ideas clear and simple.
Mostly simple. Today it's machine learning. We're looking at an academic paper.
That's right. The title is, let me get it right, Steering No Regret Agents in MFGs Under Model Uncertainty.
Yeah, quite a title. But the core idea is actually pretty intuitive, I think. Imagine like trying to guide a huge crowd, right?
Okay.
But you don't really know exactly what motivates each person or even say the layout of the streets they're walking on. That's kind of the problem, but for AI agents.
Got it. So this paper is about how some kind of central planner, a mediator, can nudge lots of independent learning agents, AI agents, when things are uncertain.
Exactly.
So our mission for this deep dive: figure out the main problem here, unpack the solutions they're proposing, which sound quite innovative, and, understand why this research is actually important for multi-agent systems, for ML.
Or your guides, yeah.
Mm.
So the paper, it dives into incentive design, specifically in mean field games, MFGs.
MFGs. Like, these aren't board games.
No, think big. Huge populations of agents interacting, like cars in traffic.
Mm-hmm.
Each one affects the flow, but only through the sort of aggregate, the mean field.
Okay. And this paper looks at giving incentives when the mediator, the one trying to guide things, doesn't know the full picture, doesn't know the rules or motivations.
Precisely. That's the model uncertainty part. Big challenge.
And the paper's big idea.
Well, they've developed these novel algorithms, ways for the mediator to offer these little nudges, these steering rewards, to guide the collective behavior towards something desirable, even with all that uncertainty. And importantly, they've got proofs, theoretical guarantees these methods work, and that the cost of paying out these rewards doesn't just skyrocket.
Which is pretty crucial. Why should our listeners care, though? What's the real world angle?
Well, think about it. So many systems involve these massive numbers of interacting parts. Financial markets, sure, but also power grids, robot swarms, maybe even online platforms.
Right.
Being able to steer these systems towards better outcomes, less congestion, more efficiency, whatever it is, that's huge. But the tricky part, as this paper points out, is doing it when you don't have perfect information, which is almost always the case in reality.
Okay, so let's rewind a bit. Give us some context. Where do mean field games come from?
Right, so MFGs, they're a mathematical framework, really, developed to handle these systems with just vast numbers of agents.
Too many to track individually.
Exactly. So instead, you look at the average effect, the mean field. How does the crowd behavior influence an individual, and how does the individual respond? It lets you analyze things like macroeconomics, traffic flow, as we said, even auctions or coordinating self-driving cars. It simplifies the complexity.
But if all these agents are just acting in their own self-interest, things can go wrong collectively, can't they?
Oh, absolutely. That's a fundamental problem. They can easily end up in what we call bad equilibria.
Like the traffic jam example. Everyone tries to get ahead, and everyone gets stuck.
Precisely. Individually rational moves leading to a collectively bad outcome. So the big question is, how do you nudge them away from those bad spots?
And that's where incentive design comes in, which is the paper's focus.
Exactly right. Incentive design is all about tweaking the rewards, changing the game slightly so that individual self-interest aligns better with the overall goal.
And the specific flavor this paper looks at is the steering problem. What's that?
So the steering problem is you have a mediator, someone outside the game, essentially, and they're trying to guide these agents who are learning and adapting over time towards certain desirable behaviors.
How?
By offering extra rewards, these steering rewards, little bonuses for doing the right thing from the mediator's perspective.
Okay, but people have thought about steering before, haven't they? What's new here?
Good point.
Yeah.
Yes, there's prior work, but a lot of it looked at much smaller groups of agents, like maybe a few robots.
Not thousands or millions.
Right. The math and computation just explodes when you scale up. That's often called the curse of multi-agency. It gets incredibly complex.
And the other limitation?
A lot of the older work just assumed the mediator knew everything, knew the exact rules of the environment, knew exactly how rewards worked, perfect information.
Which is rarely true.
Very rarely.
Yeah.
So this paper tackles both, the large scale of MFGs and this realistic assumption of model uncertainty. They're really pushing the boundary there.
Got it. And they focus on a specific type of MFG, something about transitions?
Yes, density-independent transitions. It's a common type. Basically, it means the underlying rules of how the environment changes don't directly depend on how the agents are distributed. An agent's rewards might depend on the crowd, but the environment's physics, so to speak, don't. It's a useful simplification for many systems.
Okay, so let's clarify the roles again. The mediator wants what?
The mediator wants to maximize their own utility function, which basically measures how good the overall outcome is based on the collective agent behavior, the population density.
Yeah, and the age.
The agents are just trying to maximize their own total rewards over time. That includes whatever intrinsic rewards they might have, plus the steering rewards from the mediator.
Yeah.
And crucially, they're learning. They adapt their strategies.
And they learn in a specific way. The paper assumes no adaptive regret.
Right. That's a fairly standard assumption in this area.
Yeah.
Intuitively, it means agents try to make choices that, looking back, would have been good choices given what happened in the past. They aim to minimize their regret, even as the situation evolves. It's a plausible model for adaptive agents.
Okay, now the big hurdle, model uncertainty. What exactly is the mediator uncertain about?
Two main things. First, the environment's rules the transition dynamics. How does the state change based on actions? They don't know that precisely.
Okay.
Second, the agent's own motivations, their intrinsic reward functions. What do the agents actually want, separate from the mediator's steering? They don't know that either.
Wow, okay. So steering seems really hard then. How do you guide agents if you don't know the map or their personal goals?
It's incredibly tough. The mediator has to balance learning about the system that's exploration with actually trying to guide the agents towards the goal that's exploitation. It's a classic trade-off, but in this really complex multi-agent setting.
All right, so this brings us to the novel ideas in the paper. How do they actually do the steering under this uncertainty?
Well, the core approach is pretty smart. The mediator designs the steering rewards, not just to push agents, but also to kind of deliberately gather information about the unknowns, learning by steering, essentially.
And they break it down. Let's start with a simpler case.
Yeah, they first look at steering towards a fixed target. So the mediator has a specific desired behavior pattern, a target policy in mind.
Okay.
And they show that even without knowing the full model, you could design rewards to, like, pull the agents towards that target.
If you don't know the consequences.
It seems counterintuitive, but roughly speaking, you penalize deviations. If the agents start drifting from the target behavior, the reward structure gives them a little pushback towards it. It works based on observing the behavior itself, rather than needing to perfectly model the underlying dynamics.
Interesting. Okay, now for the really new stuff. What if the agents have, like, no built-in goals, no intrinsic reward?
Right, the zero intrinsic reward case. Here they introduce something called an optimism-based exploration algorithm.
Optimism-based, how does that work?
So the mediator keeps track of a set of possible game models, all the ways the world might work, consistent with what they've seen so far.
Plausible scenarios.
Exactly. Then, when choosing steering rewards, they act optimistically. They assume the best possible scenario out of that set is true and design rewards based on that.
Why be optimistic?
It serves two purposes. One, it pushes agents towards potentially good outcomes based on the current, maybe incomplete understanding. Two, it actually encourages exploration. If your optimistic assumption is wrong, acting on it will likely lead to observations that reveal the true nature of the game faster. You learn by testing your rosy assumptions.
Clever. And does this optimistic approach actually work? Are there guarantees?
Yes, and this is really important. They provide theoretical proofs. They show that the steering gap, basically how far the agents end up from the desired behavior and the steering cost, the total rewards paid out both grow sublinearly.
Sublinearly, meaning
They grow slower than time or the number of interactions. So on average, the gap gets smaller and the cost per step goes down over the long run. It's efficient and effective. It doesn't just keep getting worse or more expensive indefinitely.
Okay, that's impressive. But what about the harder case? When agents do have their own secret motivations, their unknown intrinsic rewards.
Ah, yes. That adds a whole other layer of complexity. Now the mediator is flying blind about the environment and about what the agents actually want deep down.
So optimism probably isn't the right approach there.
Probably not. Instead, they propose a pessimism-based reward estimation strategy.
Pessimism. So they assume the worst.
Sort of. They try to estimate the agent's hidden intrinsic rewards based on observing their behavior, which is noisy and imperfect. Then, because they know their estimate isn't perfect, they act pessimistically when designing the steering rewards. They account for the uncertainty in their estimates of what the agents want.
Why pessimism here?
It makes the steering more robust. By being a bit cautious and assuming the agent's intrinsic drives might hinder the steering more than they actually do, the mediator can design incentives that are strong enough to overcome those potential motivations, even without knowing them exactly. It ensures they can still steer effectively despite the reward uncertainty.
And does this pessimism strategy also come with guarantees?
Yeah.
Even with this double uncertainty?
Remarkably, yes. They show that even in this much harder setting, their algorithms still achieve that sublinear steering gap. They can guide the agents effectively over time. And the steering cost. It remains comparable to what you'd expect from simpler strategies that don't handle this intrinsic reward uncertainty. That's quite an achievement.
Wow. And there is one other technical term, eluder dimension. What role does that play?
Right, the eluder dimension. It's a concept from learning theory. Essentially, it measures how complex the set of possible unknown functions is, in this case, the unknown intrinsic reward functions.
So higher dimension means more complex.
Exactly. A higher eluder dimension means the agent's motivations could be more varied or intricate, making it harder for the mediator to learn them accurately just from observations. It basically quantifies how difficult the reward learning part of the problem is. It affects how quickly the mediator can narrow down the possibilities.
Okay, so let's try to wrap this up. What are the main takeaways for someone listening to this deep dive?
I think the big picture is this. We now have a more powerful toolkit, a framework and actual algorithms for influencing large groups of learning agents. Crucially, these tools work even when we have incomplete information, when the system dynamics and agent motivations are partly unknown.
Which is much closer to real-world problems.
Absolutely. And that means potential applications in managing traffic, setting economic policies, coordinating autonomous systems. Anywhere you have lots of interacting agents and uncertainty, this gives us a way to potentially guide them towards better collective outcomes.
And the core innovation seems to be this really smart balancing act.
Definitely. Balancing the need to learn about the system exploration with the need to actually achieve the steering goal exploitation, using optimism when learning the environment, and pessimism when dealing with unknown motivations. That's a very neat way to handle the different types of uncertainty.
Feels like this opens doors for more research too, right? Where might this go next?
Oh, for sure. One obvious direction is tackling even more complex MFGs, like where the environment's rules do change based on the agent density. That's much harder.
Okay.
Another is finding ways to make this tiering even cheaper. Can we get the same results with less incentive cost? And of course, testing these ideas robustly in real-world, messy situations, not just simulations. That's always a key step.
It really does make you think differently about designing complex systems, doesn't it? How do we shape collective behavior for the better when we can't possibly know everything?
Exactly. It's moving away from assuming perfect control and perfect knowledge towards designing systems that can learn and adapt and guide effectively, despite uncertainty. It's a really important shift in thinking for AI and complex systems management.
Well, this has been fascinating, a real deep dive into steering agents under uncertainty. Thanks for walking us through that.
My pleasure. It's exciting stuff.
That's all for this episode of The Deep Dive. Hopefully you feel a bit more informed about this corner of machine learning research. Join us next time as we tackle another complex topic.